Welcome to this lecture series in linear algebra. In this lecture, we will learn about polyeigenvectors and generalized polyeigenvectors. These are not standard notions. I invented them just for my purpose. And let us recall what we need to follow this lecture. So earlier we have seen that if S is an endomorphism on a vector space V, then these equalities hold. Right? So the kernel of this particular exponent of S remains unaltered even if you increase the exponent any further. Alright. Last time we saw the notion of an eigenpolynomial, which was just a generalization of the notion of an eigenvalue. So what was the definition? An endomorphism T on V has been fixed. Then an irreducible monic polynomial Px over the base field is said to be an eigenpolynomial if it's, if this happens, meaning the kernel of this endomorphism is non-trivial. Right, and the connection with eigenvalues was that if lambda is an eigenvalue, then x minus lambda is an eigenpolynomial, and conversely. Okay. So what is a polyeigenvector? Fix an endomorphism on a vector space V and an eigenpolynomial of T, call it Px. We say that a vector V is a polyeigenvector of T corresponding to the eigenpolynomial Px if this happens, if V is in the kernel of Pt, right? So this is just a generalization of the notion of an eigenvector. If this was a degree 1 eigenpolynomial, meaning it was corresponding to an eigenvalue, then it would look like x minus lambda. And then a polyeigenvector would then be a vector V such that V is in kernel x minus lambda. Not x minus lambda. V is in kernel t minus lambda I, because if Px is equal to x minus lambda, then Pt is that guy, and hence this would be the meaning of V being a polyeigenvector corresponding to this particular eigenpolynomial. But that's same as saying V is an eigenvector corresponding to this eigenvalue lambda. So the notion of a polyeigenvector is an immediate generalization of the notion of an eigenvalue. All right. So let's look at an example. Last time we looked at this example, but we did not, of course, we did not talk about polyeigenvectors there. So what was the endomorphism? We have this endomorphism of R3, which on E1 and E2 behaves this way, but it fixes E3. So we commented that it is basically rotating this bottom plane. This it is keeping fixed, but it is rotating about this axis the entire 3-dimensional space. Right, and we saw that this is an eigenpolynomial of T, and a polyeigenvector would be E1. So E1 is a polyeigenvector corresponding to this particular eigenpolynomial, polyeigenvector of T, of course. So this you can just immediately check by, seeing that the kernel of this guy contains E1. That's all. So this is fine. Now we will discuss a further generalization, generalized polyeigenvectors. So fix an endomorphism T and an eigenvalue, and an eigenpolynomial of T. We say that a vector V is a generalized polyeigenvector of T corresponding to the eigenpolynomial if the vector lies in for some, right? So clearly every polyeigenvector is a generalized polyeigenvector, because if you just substitute n equals 1, then you get polyeigenvectors. But here we are having a relaxation. But at the same time, by what we recalled in the beginning, an alternate way to define generalized polyeigenvectors would be to say the following. So a vector V is a generalized polyeigenvector of T corresponding to the eigenpolynomial Px if and only if it belongs to kernel of that thing. So this is what we saw in the beginning, that the kernels do not increase beyond this point, and hence this is kind of the greatest thing for all possible n. So it's equivalent. Just to realize that this pink thing is equivalent to that thing. All right. One instantiation of the above definition is the following. Suppose lambda was an eigenvalue of T, then this would be an eigenpolynomial of T. Then the corresponding generalized polyeigenvectors are called generalized eigenvectors. So let me write this down and then say more. So fix an eigenvalue lambda of T. We say that a vector V is a generalized eigenvector of T corresponding to lambda if V lies in kernel of right? So every generalized eigenvector is a generalized polyeigenvector after all. It's just that the eigenpolynomial is a degree 1 polynomial, meaning it comes from an eigenvalue. And this is a standard terminology. This you can find in textbooks. Somehow people do not talk about this, but I think it is a natural notion. And as of now, we are just discussing some definitions, but this is going towards a very general structure theory. So just hang tight. So yeah, so this comment is basically, this comment is basically saying that every generalized eigenvector is a generalized polyeigenvector. Okay. So now let's just look at an example of a generalized eigenvector, which is not an eigenvector. So it is a generalized eigenvector, but not an eigenvector. So that is what we want to see. So fix an endomorphism of R2 defined via these equations. It fixes E1, but E2 is moved to this particular point, E1 plus E2. And we have drawn a separate vector V. We will talk about that. But note that 1 is an eigenvalue of T because of this equation. All right. Now take any vector V of this form. So its second coordinate is 1 and the first coordinate is whatever. So let's say V is equal to A E1 plus E2. So first of all, this is not an eigenvector corresponding to eigenvalue 1. This is not an eigenvector simply because T minus identity of V is this. Right? But this is 0 because E1 is fixed by T and by I also, of course. So this is equal to the second part. But if you calculate this, you get TE2 minus E2, which is E1 by definition of T. So this is non-zero, and hence V is not an eigenvector corresponding to eigenvalue 1. But one more application of T minus I gives you 0, because again T is fixed by, E1 is fixed by T as well as identity. So anything of this form is a generalized eigenvector of T corresponding to the eigenvalue 1, but not an eigenvector. And in fact, everything in R2 is a generalized eigenvector corresponding to this eigenvalue, right? Even if I had written a B over here, it would still get killed by t minus I whole square. But some of those things happen to be eigenvectors, like things here. These things here are eigenvectors as well as, of course, generalized eigenvectors, because every eigenvector is a generalized eigenvector, but not every generalized eigenvector is an eigenvector. Fine, so I hope this example was illustrative.
Okay, so now let us see an example of generalized polyeigenvectors, a genuine example of it. Okay, so what we have here is the standard basis of R4. We have named it a little differently than we usually do. We use E1 for this, E2 for that, and so on, but I have named it a little differently. And define a linear map from R4 to R4, a linear endomorphism on R4 basically, via these equations. So to define a linear map, we just need to prescribe what it does on the basis elements. And the basis we have chosen is the standard basis. And this is how we define the linear map. So note that the subspace generated by U0 and U1 is invariant, right? Because U0 maps to the span of U0 and U1, and U1 also maps in the span of U0 and U1. So this particular subspace is T invariant. And then there is a little bit more complicated behavior on the remaining two basis elements. But in the matrix form, it looks like this. So the matrix of T with respect to this basis, I should technically write down the basis with respect to which this matrix is formed. But I have chosen not to do that for the sake of brevity. So this is the matrix of T with respect to this particular basis in that order. So the basis is ordered like that. All right. And let us note that the minimal polynomial of T is this guy. Now you can do this via kind of a brute force computation. Just check that this guy is satisfied by T. And since this thing inside is irreducible, there are only two candidates for the minimal polynomial. Either it is going to be this or it is going to be that. And you can check that this is not the minimal polynomial because T does not satisfy the thing inside. So the minimal polynomial has to be that. But there is a somewhat more systematic or less computational way of doing it. So first, just show that the minimal polynomial of the restriction of T to the span of U0 and U1, the minimal polynomial of this guy is this thing. That you can do by pure computation. It is going to be a very short computation because this is just a two-dimensional vector space that we are dealing with. And now if you take the quotient space, the corresponding operator on the coset space, the quotient space, not the coset space, the corresponding linear map on the quotient space also has a minimal polynomial that much. Because if you just look at the description of the corresponding endomorphism, it looks exactly like that in a certain sense. So I'll let you figure that out. So the endomorphism on the quotient also has minimal polynomial that. And now since the minimal polynomial of T divides the product of the minimal polynomial on the restriction and the minimal polynomial of the endomorphism on the quotient. Sorry, let me write that again. So this thing divides the product of these two things, the minimal polynomial of the restriction and that of the endomorphism on the quotient. This thing is equal to that. So therefore we deduce that the minimal polynomial of T either is equal to this or is equal to the thing inside. But it cannot be the thing inside because T does not satisfy the thing inside. You can check that on V1. V1 is a witness that T does not satisfy this polynomial. So this is basically an exercise for you to figure out that the minimal polynomial of T is equal to this much. But I've given some details verbally. Okay, and now since we know that what are the eigenpolynomials are precisely the irreducible factors of the minimal polynomial. We see that the endomorphism T has only one eigenpolynomial, namely this thing. So let me record that. The only eigenpolynomial of the endomorphism T is this particular polynomial. Okay, and now note that V1 is a generalized Polyeigenvector of T corresponding to this polynomial, because everything is a generalized eigenpolynomial of T corresponding to this polynomial, this eigenpolynomial, because this thing kills everything in the vector space V. This being the minimal polynomial kills everything in the vector space V, and hence everything is a generalized Polyeigenvector corresponding to this eigenpolynomial. So this statement is rather trivial once we know that the minimal polynomial of T is this guy. But you can check just by a simple computation that V1 is not an eigenpolynomial, even though it is a generalized eigenpolynomial. It is not an eigenpolynomial of T corresponding to this guy. What have I written? It is not a Polyeigenvector. I said something wrong and I wrote something wrong. I had written something completely meaningless. We see that V1 is a generalized Polyeigenvector of T corresponding to this eigenpolynomial, but V1 is not a Polyeigenvector corresponding to this eigenpolynomial. So here I wanted to write Polyeigenvector. Right, so V1 is not a Polyeigenvector of T corresponding to this eigenpolynomial, simply because if you just compute, this thing is non-zero. That's a matter of computation. So I just wanted to illustrate a genuine example of a generalized Polyeigenvector, which is not a Polyeigenvector. Every Polyeigenvector is a generalized Polyeigenvector, trivially, but I just wanted to give an example where the distinction is clear. And this is a fairly rich example. Usually the examples we see is just rotation in R2, etc. But I wanted to give a rich example, and this is one good example. Okay, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.